Welcome! In this session, we'll tackle LeetCode problem number 945, minimum increment to make array unique. This problem challenges us to modify an array so that all its elements are unique with the minimum number of increments. Let's dive into the solution step by step and explore the best approach. In this problem, you're given an integer array called nums. Your task is to make all the values in the array unique. To do this, you can increment any element in the array by 1 as many times as needed. For example, if an element is 2, you can change it to 3 in one move. The goal is to determine the minimum number of moves required to make all the elements in the array unique. For the input, you'll receive an integer array nums of length n. And the output will be a single integer, which represents the minimum number of moves needed. To help clarify, let's look at some examples. In the first example, the input array is 1, 2, 2. The output is 1, as you can increase one of the 2's to 3, making the array 1, 2, 3. Only one move is needed to achieve uniqueness. In the second example, the input array is 3, 2, 1, 2, 1, 7. Here, the output is 6. This is because we need 6 increments in total to make all elements unique. For instance, after performing the moves, the array could look like 3, 4, 1, 2, 5, 7. Notice that the final array does not need to be sorted, only unique. Now, consider the third example where the input array is 0, 0, 0. In this case, the output is 3. Starting with 3 zeros, you can increment the second 0 to 1 and the third 0 to 2, resulting in the array 0, 1, 2. This requires 3 moves in total, making all the elements unique. Let's also discuss the constraints and some important edge cases. The array length, nums.length, can range from 1 to 10^5, and each element in the array can range from 0 to 10^5. This means the solution needs to be efficient enough to handle large inputs. For edge cases, if nums contains only one element, no moves are needed because a single element is already unique. Similarly, if all the elements in the array are already unique, no moves are required. Additionally, the array can include zeros, duplicate values, or very large numbers. The solution must account for these scenarios and compute the result optimally, even at the upper limit of the constraints. To solve the problem of ensuring all numbers in an array are unique with the minimum number of increments, we considered several approaches. The first is the brute force approach. The intuition here is simple: whenever we encounter a duplicate number, we increment it until it becomes unique. This involves repeatedly scanning the array to find the next available number for each duplicate. While straightforward to implement, this method is highly inefficient for large arrays since each duplicate requires a linear scan to resolve. As a result, the time complexity becomes n squared, which makes it unsuitable for larger inputs. Although simple, the trade-off is the significant performance hit due to repeated checks for duplicates. An alternative approach is to leverage sorting. By sorting the array, duplicate values naturally align consecutively, making it much easier to resolve them. After sorting, we can traverse the array and increment any duplicate values to ensure that each number is at least one greater than the previous. This eliminates the need for repeated scans, as we handle duplicates in a single pass. The complexity of this method is dominated by the sorting step, which takes n log n, followed by a linear traversal, resulting in an overall complexity of n log n. This is a significant improvement over brute force. It is also intuitive and relatively simple to implement. However, one drawback is that sorting the array might not be strictly necessary, as there are alternative methods that avoid this step entirely. Another approach we considered is using counting sort. This method takes advantage of the fact that the input consists of non-negative integers. By creating a frequency map, we can directly track how many times each number appears. As we iterate through the frequency data, duplicates can be resolved by assigning the next available number, while also keeping track of the total increments required. The time complexity here is n, for counting the frequencies, plus an additional cost proportional to the largest number in the array, referred to as max_val, for resolving duplicates. This gives an overall complexity of n plus max_val. While this is faster than the sorting-based approach for arrays with small ranges of values, it requires extra space for the frequency map. This trade-off makes it less appealing for cases where the range of numbers is very large. Ultimately, we chose the sorting-based approach due to its balance of simplicity and efficiency. Unlike the brute force method, it avoids repeated scans of the array, and compared to counting sort, it doesn't require additional space to maintain a frequency map. Sorting the array aligns duplicate numbers consecutively, allowing us to resolve conflicts in a single linear traversal. This makes the implementation both clean and efficient. The key insight here is that sorting provides a natural order that simplifies the process of ensuring uniqueness, eliminating the need for more complex or memory-intensive solutions. The final algorithm involves 3 steps. First, sort the array. Second, traverse it to ensure each number is strictly greater than the previous one, incrementing as needed, and third, return the total count of increments. This approach achieves a time complexity of n log n, and is well suited for the problem constraints, offering a practical and robust solution for most input sizes. To solve this problem, we need to ensure that all elements in the array are unique, and we want to achieve this with the minimum number of increments. The key idea is to leverage sorting and a greedy approach. By sorting the array first, we can easily identify duplicates since they will be adjacent. For example, if the input array is 3, 2, 1, 2, 1, 7, sorting it gives us 1, 1, 2, 2, 3, 7. This makes it clear where the duplicates are and allows us to resolve conflicts systematically. Sorting is efficient, with a time complexity of n log n, when using algorithms like timsort, which is the default for Python's built-in sort, or sorted, functions. Now that we have the array sorted, we can proceed to the next steps to make the elements unique. Once the array is sorted, the next step is to initialize 2 key variables. First, we set moves to 0, which will track the total number of increments needed. Second, we initialize previous to the first element of the sorted array, nums, 0, to keep track of the largest unique value encountered so far. With these variables in place, we'll iterate through the array starting from the second element, comparing each value to previous. If the current value is greater than previous, no increment is needed, and previous is simply updated to the current value. However, if the current value is less than or equal to previous, it means there's a conflict. In this case, we calculate the number of increments required to make the current value unique, which is previous plus 1. We then add the difference between previous plus 1 and the current value to moves, and update previous to this new unique value. This approach ensures that all conflicts are resolved incrementally and efficiently. To understand this process better, let's walk through an example. Starting with the sorted array 1, 1, 2, 2, 3, 7, we initialize moves to 0 and previous to 1. In the first iteration, the second element is also 1, which creates a conflict. To resolve it, we increment the value to 2, add 1 to moves, and update previous to 2. Moving to the next element, which is 2, we have another conflict because it's not greater than previous. Here, we increment the value to 3, add 1 to moves, and update previous to 3. The next element is another 2, which requires 2 increments to become 4. We add 2 to moves and update previous to 4. Similarly, the next element is 3, which is increment twice to 5, adding another 2 to moves and setting previous to 5. Finally, the last element, 7, is already greater than previous, so no increment is needed, and previous is updated to 7. At the end of the loop, the array becomes 1, 2, 3, 4, 5, 7, and the total number of increments, stored in moves, is 6. This value is then returned as the result. Now, let's dive into some key insights about this approach. First, sorting plays a crucial role in simplifying the problem. By grouping duplicates together, sorting allows us to resolve conflicts in a systematic way, avoiding the need for additional checks or operations. Without sorting, identifying duplicates and resolving them would be much more complex and computationally expensive. Second, this algorithm uses a greedy strategy, where we always resolve conflicts by incrementing to the smallest possible unique value, which is previous plus 1. This minimizes the total number of increments required and ensures an optimal solution. In terms of efficiency, the sorting step has a time complexity of n log n, while the iteration through the array is n. Combining these, the overall complexity of the algorithm is O, n log n, making it efficient for large inputs. When implementing this algorithm, it's important to consider edge cases that could affect its behavior. For instance, if the input array is empty, there are no elements to process, so the function should simply return 0 since no increments are needed. Another edge case is when all elements in the array are already unique. In this scenario, sorting and iterating through the array will not result in any increments, and the moves variable will remain 0. Finally, if there are many duplicate values in the array, the algorithm efficiently handles them by incrementing each duplicate to the next available unique value. This incremental approach ensures that even large numbers of duplicates are resolved without excessive computational overhead. Additionally, the algorithm modifies the array in place, which reduces space usage, though it's also possible to work with a copy of the array if immutability is required. The variables moves and previous are the only additional memory used, keeping the space complexity low. In conclusion, the algorithm achieves a time complexity of O, n log n, which is driven by the sorting step. The subsequent iteration through the array is linear, O, n, and does not dominate the overall runtime. As for space complexity, if the array is sorted in place, the algorithm uses O1 additional space. If a copy of the array is used for sorting, the space complexity increases to O, n. This combination of time and space efficiency makes the algorithm well-suited for solving the problem of minimizing increments to make an array unique, even for larger inputs. This implementation solves the problem of making an array unique with minimal increments. The key idea is to sort the array and then use a greedy approach to resolve duplicates. We start by sorting the input array nums. Sorting ensures that any duplicate or conflicting values are adjacent, making it easier to identify where increments are needed. Sorting is O, n log n, in terms of time complexity. Next, we initialize two variables. The moves variable will track the total number of increments required, and previous will keep the previous processed value. This helps us enforce the condition where each element in the array is unique. Initially, previous is set to the first element of the sorted array, or 0 if the array is empty. The algorithm then iterates through the sorted array starting from the second element. For each element, we check if it is less than or equal to the previous value. If it is, we calculate the required increments to make the current value strictly greater than previous, i.e., previous plus 1. These increments are added to the moves counter, and previous is updated to reflect the new unique value. If the current value is already greater than previous, we simply update previous to this value without adding any increments. By the end of the loop, all array elements are unique, and the moves variable contains the total number of increments made. The overall time complexity is dominated by the sorting step, which is O, n log n, and the space complexity is O1, since no additional data structures are used apart from a few variables. This solution is efficient, concise, and handles edge cases like empty arrays or arrays with all unique elements naturally. This is the Java implementation for LeetCode problem number 945, minimum increment to make array unique. The logic mirrors the Python solution, where the array is sorted first to handle duplicates effectively. The algorithm iterates through the array, ensuring each element is adjusted to be unique by incrementing it as needed. Key differences include Java's use of type declarations and the arrays.sort method for sorting. The solution maintains clarity and adheres to Java conventions. To solve this problem, we begin by sorting the input array. This step ensures that all duplicates are grouped together, making it easier to process the elements sequentially. After sorting, our array becomes 1, 1, 2, 2, 3, 7. Next, we initialize two variables. The first is moves, which starts at 0 and will keep track of the total number of increments we make. The second is previous, which is set to the first element of the sorted array, in this case, 1. Previous will help us track the last unique value as we iterate through the array. Now, as we process each element, we check if the current value is less than or equal to previous. If it is, we increment the current value to make it greater than previous. For example, at index 1, the value is 1, which is equal to previous. We increment it to 2, add the difference of 1 to moves, and update previous to 2. Similarly, we handle the next elements, incrementing as necessary to ensure uniqueness. By the end of this process, the total moves required is 6, which is our result. In this case, the input array is 1, 1, 1. Since the array is already sorted, we can skip the sorting step and move directly to initializing our variables. We set moves to 0 and previous to the first element of the array, which is 1. Now, we process each element one by one. At index 1, the value is 1, which is equal to previous. To make it unique, we increment it to 2, add the difference of 1 to moves, and update previous to 2. At index 2, the value is again 1, which is less than previous. We increment it to 3, add the difference of 2 to moves, bringing the total to 3, and update previous to 3. Since there are no more elements to process, the final output is 3, which represents the total number of increments needed to make all elements unique. Here, the input array is 0, 2, 2, 2, 4. After sorting, the array becomes 0, 2, 2, 2, 4. We initialize moves to 0 and previous to the first element of the array, which is 0. Now, we start processing the elements. At index 1, the value is 2, which is greater than previous, so no increment is needed. We simply update previous to 2. At index 2, the value is 2, which is equal to previous. To make it unique, we increment it to 3, add the difference of 1 to moves, and update previous to 3. At index 3, the value is again 2, which is less than previous. We increment it to 4, add the difference of 2 to moves, making the total 3, and update previous to 4. Finally, at index 4, the value is 4, which is equal to previous. We increment it to 5, add the difference of 1 to moves, bringing the total to 4, and update previous to 5. The final output, representing the total number of increments required, is 4. To analyze the time complexity of our solution, we begin with the sorting step. Sorting the array using Python's built-in sort function is the most computationally expensive operation, requiring O and log n time, where n is the number of elements in the input array. Once the array is sorted, we iterate through it using a for loop. Each iteration processes one element and performs constant time operations such as comparisons and arithmetic updates. This iteration step, therefore, contributes O, n, to the overall complexity. Finally, the operations inside the loop, like checking and incrementing values, are basic arithmetic tasks that individually take O(1) time. Since these operations are applied to each element only once, they collectively add up to O(n) as well. Now looking at the overall time complexity, the sorting step, which takes O and log n, is the dominant term. While the for loop and the operations within it contribute O(n), this is asymptotically smaller compared to the sorting step. As a result, the overall time complexity of the function is determined by the sorting step, making it O and log n ***. Shifting to space complexity, the input array nums occupies O(n) space. Sorting the array might require additional memory depending on the sorting algorithm. Python's timsort, for example, has a worst-case space complexity of O(n) for temporary storage. Beyond this, the function uses only a few auxiliary variables such as moves and previous, which take constant space, or O(1). These additional factors are negligible compared to the space required for the input and sorting. Considering the overall space complexity, the dominant factor is the space used by the input array in the sorting process, resulting in a total space complexity of O(n). Let's now analyze best, average, and worst-case scenarios. In the best case, where all elements in nums are already unique, the algorithm still sorts the array, which takes O and log n. Since no increments are needed, the for loop contributes only O(n). Thus, the best case complexity remains O and log n ***. For the average case, some duplicates are present, leading to additional operations during the loop. However, these are linear and do not change the dominant term, so the average case complexity is still O and log n ***. Finally, in the worst case, if all elements in the array are identical, the sorting step is still O and log n, and the loop resolves all duplicates in O(n). Even here, the overall complexity does not exceed O and log n ***. To better understand the efficiency of our approach, let's compare it to a naive, brute force method. The naive approach involves repeatedly checking for duplicates and incrementing elements until all values are unique. Each duplicate check and increment can take up to O(n) time, leading to a worst-case time complexity of O(n squared). This is significantly less efficient than the sorting-based approach. By sorting the array first, duplicates are grouped together, and we can resolve conflicts in a single pass. This reduces the time complexity to O(n asterisk log n asterisk asterisk), a dramatic improvement over O(n squared). The big O analysis confirms this. The sorting step dominates the overall complexity at O(n asterisk log n asterisk asterisk), while the single pass loop adds only O(n). Combining these, the total complexity is O(n asterisk log n asterisk asterisk), making the algorithm both efficient and scalable. When solving this problem, there are several common mistakes to watch out for. First, not sorting the array is a frequent error. Sorting is crucial because it allows us to systematically address duplicates by incrementing them in sequence. Without sorting, the process of resolving duplicates becomes chaotic and inefficient. Another mistake is using nested loops for conflict resolution. While this approach might seem intuitive, it results in an O(n squared) time complexity, which is impractical for large input sizes. Sorting the array allows us to achieve a much more efficient O(n log n) solution. Additionally, edge cases are often overlooked. Examples include situations like dealing with an empty array, arrays where all elements are already unique, or arrays with very large values. Missing these scenarios can lead to runtime errors or incorrect results. There's also a risk of overcomplicating the logic for resolving duplicates. Some solutions attempt to track all used numbers in a set, which unnecessarily increases space complexity. A simpler greedy approach is usually sufficient. Finally, it's important to validate input constraints. For instance, ensuring that all numbers are integers within the specified range prevents assumptions that could cause the solution to fail unexpectedly. Now, let's explore some key insights for tackling this problem effectively in interviews. The most efficient method combines sorting the array with a greedy approach to resolve duplicates. By iterating through the array and ensuring that each element is at least one greater than the previous, we minimize the number of increments required. This approach is systematic and aligns with the problem's constraints. A useful pattern to remember is that problems involving uniqueness often benefit from sorting and greedy strategies, as they allow for structured conflict resolution. During an interview, you might be asked to explain why this greedy approach works and why sorting is necessary. It's a good idea to be prepared to discuss the trade-offs, such as the O(n log n) time complexity of the sorting-based solution versus the potential of a hash-based approach with O(n) complexity for counting. Clear communication is also essential. Be sure to articulate edge cases and how your solution accounts for them. This demonstrates your attention to detail and ensures the interviewer understands the robustness of your approach. Next, let's discuss how this problem connects to related challenges and explore alternative approaches. Some related problems where greedy algorithms and sorting play a key role include LeetCode 56, merge intervals, which involves resolving overlaps, LeetCode 452, minimum number of arrows to burst balloons, another interval-based problem, LeetCode 1029, two-city scheduling, which uses a greedy strategy with sorting, and LeetCode 1094, carpooling, which deals with efficiently tracking and resolving overlaps. These problems highlight the versatility of greedy algorithms. As for alternative approaches, one option is using a hash map for frequency counting. Here, you count the occurrences of each number, then resolve duplicates by identifying the next available number. This method has a time complexity of O(n) for counting plus O(u) log u for resolving, where u is the number of unique integers. However, it may require more space compared to the sorting-based approach. Another alternative is brute force, checking each element against all others and incrementing duplicates as needed. While simple, this approach has an O(n squared) time complexity, making it only practical for very small input sizes. Finally, another alternative to consider is using bucket sort. This approach involves creating a bucket frequency array to resolve duplicates. If the range of values in the array is small, bucket sort can achieve an O(n) time complexity, making it highly efficient. However, the trade-off comes in the form of increased space complexity, which grows with the range of values. This method is particularly useful when you need to optimize time and can allocate additional space. Overall, each alternative has its strengths and weaknesses, and the choice of approach often depends on the specific constraints of the problem you're solving. Understanding these trade-offs and explaining them clearly can set you apart in interviews, as it demonstrates both technical knowledge and problem-solving versatility. To wrap up, we reviewed how to approach the problem, focusing on a greedy strategy with sorting. Remember the importance of pre-processing and edge case analysis. Thanks for joining, and don't forget to like and subscribe for more coding problem solutions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!